In our last lecture, we talked about series reactions and yield. And here we're going to take this concept of different reaction pathways and the measurement of which product you form maybe a step further. And we're going to do that by talking about parallel reactions and selectivity. And what I mean by a parallel reaction is that you're going to start with, some product or some reactant A, and it has the ability to undergo two processes. So you're going to make the desired product D or the undesired product U, okay? And obviously these two things are happening in parallel. And in the last lecture, where yield really focused on what portion of A becomes the desired product, right? It really was zoomed in on here. Selectivity is going to be a comparative measure between how much of D you form versus how much of U that you form. And so there are two different kinds of selectivity that we're going to talk about in class today. So the first kind is called instantaneous selectivity. And it has the symbol S, and then it is a ratio of the desired and the undesired product. So here's SD/U, and that is defined as the rate that you form the desired product over the rate that you form the undesired product. We also are going to look at the overall selectivity, and that is SDU, again with the little squiggle over the top of it. And that is going to be a measure of the number of moles of the desired product divided by the number of moles of the undesired product. So these are the two types of selectivity that are defined in your book. They're the ones that we'll ask questions about the most. You should know, just for the future as well, that sometimes people also talk about the percent selectivity. And that is 100 times the number of moles of the desired product over the total number of moles, which in this case would be the desired product plus the undesired product. And if we want to make it a little more universal, we could actually say the sum of all the undesired products, because there's nothing that stops A from being able to undergo many, many reactions. In this case, we'll just stick with N sub U to be consistent with this mechanism here on the upper left, okay? So we're gonna do a couple of examples today where we find the concentration of desired and undesired products as a function of time. We're also gonna solve for the selectivity and the overall, or the instantaneous and the overall selectivity. But the thing to remember here is that, and I already said this once, but yield is ND versus NA, right? It's how much of A became, or how much of A has reacted, essentially, and given you what you have. Whereas selectivity is the desired product versus the undesired product. So it's not as focused on the concentration of A, but more so just on the relative concentration of those two things. So it is very possible, for example, to have a process where the selectivity is extremely high, but the yield is extremely low. For example, if the rate of reaction was very, very slow and you let the reaction go for a shorter amount of time, you might be able to have a really high selectivity, but have a very low yield, okay? So these are just our notes to get us started, maybe 10 minutes on what selectivity is and the type of problems we're going to be looking at today. And our first example problem is essentially this problem: to calculate the instantaneous and overall selectivity for the formation of B if A goes to B, and B is the desired product, and A goes to C, and we have these two reaction rate constants. We can assume that initially we have an ideal 3-liter batch reactor that only contains a 2 molar solution of A, and the concentration of B and C at the beginning are equal to 0. All right, so let's solve this problem. And we're going to set it up exactly like we just had above, except here we're going to have A goes to B instead of U, or D, sorry, and then A goes to C instead of U. Okay, so the first thing that we should do when we're confronted with a new problem is think about what are the rate laws for the 3 species in this reaction. So I'm going to ask you guys, let's find RA, RB, and RC. And so someone come in, you can give me any of the 3 that you want.
I'll say that RC is K2 times CA.
That is correct. Good job. Right? So we know that C is only formed from that reaction, and it is formed at a rate of that's equal to K2 times Ca. I like that. All right, so I'll also then take B, because then it's sort of obvious then that this one is K1 times Ca. So then what would Ra be equal to?
I had RA was negative K1 Ca minus K2 Ca.
That's correct, right? So the rate law for each of these individual reactions for A would be K1 times Ca, K2 times Ca. So we're just trying to follow the path, all the pathways that A could react. And of course, when we wrote these, we assumed that both reactions are elementary, right? And that's totally fine. So now we have the rate laws for A, B, and C. And remember, our mole balance for an ideal batch reactor is that dNi dt is equal to Ri times V, right? And if we assume that we have this constant volume batch reactor, which we were told that the volume was 3 liters, that we can divide by the volume. And so we get dCi dt is equal to Ri, right? And that's at V is equal to a constant, right? Which of course wasn't the case for one of the problems on the homework this time where you had a semi-batch reactor. So that problem was difficult, and you should definitely pay attention to what is done with that in the recitation. But now from here, we can write our 3 equations, right? So this is really 3 equations. And we know that dCa dt is equal to Ra, which is equal to minus K1 times Ca minus K2 times Ca. And if we want to, we can collect those and say that dCa dt is equal to minus K1 plus K2 times Ca. And if we went to solve this, I think that would be relatively straightforward, because we've already solved this problem before where dCa dt was equal to minus some constant times Ca, right? So this is the same problem, except instead of having just K1, as we did for A goes to B, we have K1 plus K2. And so if we want to do this, let's divide both sides of this equation by Ca and multiply both sides by dt, and we end up getting dCa over Ca equals minus K1 plus K2 times dt. And of course, we can integrate both sides, and this starts from the initial concentration to the final concentration, and that is from time equal to 0 to some time in the future. And if we do that, we get essentially the same solution we had before, was that Ca is equal to Ca0 times the exponent of minus K1 plus K2 times time, right? And there's our concentration of Ca as a function of time, which was the same integral that we did before. So now let's solve for B and C. Well, the concentration of B then, or dCb dt, we said was equal to Rb, and that was correctly K1 times Ca, right? So we can easily solve this by putting in the expression for CA, which is CA0 times the exponent of minus K1 plus K2 times time, right? And we're going to do the same thing here that we did above. So we are going to actually first multiply by dt. So we get dCB equals K1 CA0 times the exponent of minus K1 plus K2 times time dt. And we can now integrate from CB0 to CB and integrate again from 0 to t. But we know that the concentration of CB at the beginning is equal to 0. That was in the problem statement. And so let's do that. Well, this just becomes CB on the left-hand side of the equation. And then this is equal to, remember the integral of the exponent, right? If you had the exponent of AT, right? The integral of that is 1 over A times the exponent of A times time. So we're going to use that here, and we end up having to divide by minus K1 plus K2. And so we find then that this is equal to minus K1 CA0 over K1 plus K2 times the exponent of minus K1 plus K2 times time, evaluated from 0 to t. And that means that CB equals, and if we just think about what this is going to be for a second. So when we evaluate to t, we're going to get this as our expression. But at this initial condition, at 0, well, the exponent of 0 is 1. So we're just going to be left with that. And so our final solution here is that CB equals K1 CA0 over K1 plus K2 times 1 minus the exponent of K1 plus K2. Oops, I said K1, I wrote K2 times time. Okay, and there's our concentration for B as a function of time. Now to find C, we know dCC dt is equal to RC, which was K2 times CA. Now, if you look at this, these expressions are very, very similar, right? This one is K1 times CA. That one's just K2 times CA. And the way that that manifests itself here was that, remember, this just ended up being K1. So we could do the exact same math for the concentration of C, and you'd find that the concentration of C then is K2 times CA0 over K1 plus K2 times 1 minus the exponent of minus K1 plus K2 times time. Okay. And now we've found for this simple case where A can either go to B or C, both through elementary first order reactions, we were able to solve this problem. Okay. So now what we can do after we solve for the concentrations is that you'll almost always be asked to plot them. Okay. And here I'll show the plots for the concentration of A, the concentration of B, and the concentration of C as a function of time. And of course, it's not surprising that A follows this exponential decay, right? Because we have that functional form in our solution. Also, B increases at a faster rate, and we end up with a final concentration of B that is higher than the concentration of C. And that also should not be surprising, given what we know about the problem here, where K1 was higher than K2. So the first reaction, the desired reaction, should happen faster than the undesired reaction. And from here, we could ask ourselves a new question that we wouldn't have asked ourselves the last time. What is the selectivity? Okay, so let's calculate the overall, or the instantaneous selectivity first. So the instantaneous selectivity for B versus C, since B was our desired product, right? That's just the rate of B over the rate of C. And that is K1 times CA over K2 times CA. Well, those CAs cancel, and you get that the selectivity of B versus C is simply K1 divided by K2. And we can do the same thing for the overall selectivity, right? So the overall selectivity of B and C was just NB over NC, which is of course just the concentration of B times the volume over the concentration of C times the volume. And if those cancel, you get CB over CC. And we have expressions for this above, and they're huge. So it's, K1 CA0 over K1 plus K2 times 1 minus the exponent of minus K1 plus K2 times time, divided by K2 CA0 over K1 plus K2 times 1 minus the exponent of minus K1 plus K2 times time, okay? And even though that might look somewhat daunting, well, those cancel, and those cancel. And so we end up with this expression for the overall selectivity, also for this very simple reaction of K1 divided by K2. And if that's the case, right, we have K1 over K2, well, these are constants. So that means when we plot this, right, the overall selectivity, we just have a straight line with this particular reaction, okay? So if our selectivity is always the same, and here, of course, the overall and the instantaneous selectivity is the same, how would we go about manipulating the selectivity if it is dependent on the relative magnitude of the rate constants? Well, we could do this the same way we talked about in the previous lecture for yield, that we know that K1 over K2 is just equal to K10 over K20 times the exponent of minus the activation energy for reaction 1 over RT divided by the exponent of minus the activation energy for reaction 2 divided by RT, right? And we end up getting an expression for K1 over K2 as equal to K10 over K20 times the exponent of EA2 minus EA1 divided by RT. And just like the yield that we discussed in the previous lecture, the relative magnitude of these activation energies will decide how the selectivity is going to shift. So if we want the selectivity to go up, obviously we want this to become larger. So if the activation energy for reaction 2 is greater than the activation energy for reaction 1, well, we're going to want to then decrease the temperature, right? Because that will make the magnitude of that increase. And if the activation energy for the undesired reaction is less than the activation energy for the desired reaction, then what we want to do is we want to increase the temperature, okay? And this is exactly what we talked about in the last lecture for yield. While we're also talking about how temperatures have the ability to manipulate reaction rate constants, I do want to touch on one thing really, really quickly, because we're going to use it later on in the semester. And it is, how would you use a reaction rate that you know to determine the reaction rate at some second temperature? Well, for any individual reaction, right, let's just call that Ki, right? Ki as a function of temperature is just the frequency factor multiplied by the activation energy, right? EA over RT, right? At least if it has an Arrhenius form. Well, what we can do then is figure out the expression for this reaction rate constant at any particular temperature. So I could say that Ki at T2 was equal to Ki0 times the exponent of minus EA over RT2. I could do the same thing for some other temperature, T1, and say that's equal to Ki0 times the exponent of minus EA over RT1. And now I can divide these two by each other. And you get Ki at T2 over Ki at T1 equals Ki0 times the exponent of minus EA over RT2 divided by Ki0 times the exponent of minus EA over RT1. If you look at this, those two are going to cancel. And we end up with Ki at T2 over Ki at T1 equals the exponent of EA over R times 1 over T1 minus 1 over T2. Or Ki at T2 equals Ki at T1 times the exponent of EA over R times 1 over T1 minus 1 over T2. And we're going to end up using this expression a lot later on in the semester. So far we've assumed all of the reactors that we're looking at are isothermal, but that's not always going to be the case. And once we lift that assumption, we'll have to use that in order to determine the reaction rate constant as it changes with temperature. So it's not something we're going to have to do now, but we have talked about manipulating temperature as a way to increase yield and selectivity. And if we're going to do that, I think it's good for us to have some sort of feeling for how the reaction rate constants themselves will individually change as the temperature changes, okay? So in this first example today, we've solved our first parallel reaction scheme. We've developed expressions for the concentration of all the products and the reactants, and talked a little bit about how to calculate the selectivity. So before we move on to our second example today, does anybody have any questions that they would like to ask? Okay, so if that's the case, let's go ahead and move on to our second example today, all right? And example 2 asks us to find the instantaneous and overall selectivity for the formation of B if we know that A goes to B and 2A goes to C. We know that these reactions are elementary, and we also know their reaction rate constants and the initial concentration of A, okay? All right, so if we move on to this new example problem and we write our reaction scheme, what's the next thing that we should do, right? What was the thing that we did in the previous problem?
Found the reaction rates.
Exactly. So let's do the exact same thing here. Let's find RA, RB, and RC, okay? I like that. So find the rate law. That's a great first thing to do, okay? So what's the rate law for A?
I have negative K1 CA minus K2 CA squared.
Great, perfect. That's exactly what I also have. All right, so that's A. So what about B? Does someone want to come in and help us with B?
It'd be just K1 CA.
Absolutely. Very good. And now what about C?
K2 CA squared.
Almost. Does anyone want to help? That's almost correct.
Minus.
Nope, it doesn't need a negative. It's formed. So does anyone want to help?
Is it just K2CA?
No. So if this is an elementary reaction, CA squared is correct. What else are we missing here? What did we not take into account about the reaction? So for every molecule of A that's reacted, how much C do you get?
1 mole. Or every 2 moles of A is 1 mole of C.
So-
do you need to do the RA over the stoichiometric coefficient comparison?
So that's one good way to do this, right? You could say for reaction 2 that RA over the stoichiometric coefficient for A would equal RC over the stoichiometric coefficient for C. And if you look at that, well, that would mean RA over minus 2 equals RC over 1. So RC for that reaction has to equal 1/2 or minus 1/2 times RA. So for every molecule of A that reacts in this reaction, you only get 1/2 mole of C. And that's all that this is saying with the stoichiometry. So that is 1/2. So, be mindful of the reaction stoichiometry if you can. Okay. So now we have the relative rates of consumption for A and the formation of B and C, which means that we should be able to come up with a expression for the instantaneous selectivity. So let's do that. So the instantaneous selectivity of B over C is equal to RB over RC, right? And that is equal to K1 times CA divided by 1/2 K2 CA squared. So if we look at what is going to go away here, well, that CA is going to get rid of the squared, and we end up with 2K1 over K2 times CA. So now the selectivity is not going to be a constant as it was in the previous problem. So that's interesting. And the overall selectivity of B over C, of course, is NB over NC. And that's just the concentration of B times the volume over the concentration of C times the volume, right? The volumes cancel and you get CB over CC. And in the last example, we then found an expression for the concentration of CB and CC as a function of time in order to determine the instantaneous, the overall selectivity. And it is interesting to me that the overall selectivity, only depends here on the products, but here for the instantaneous selectivity, it only depends on the concentration of the reactant. So one of the things that we should be able to see right away is that, yes, to manipulate the instantaneous selectivity, we can play with the rate constants just like we have before. But the other thing that we could do that we haven't talked about before is if we really were interested in the selectivity as a driving factor for the process, we actually could just use a dilute concentration for A, and that would facilitate a much higher selectivity towards B. Okay, so that's one interesting thing that we haven't talked about before, is having the ability to use the concentration of a reactant to drive yield or selectivity. So anyway, I thought that was kind of interesting. Also, when we end up finding the concentrations of A, B, and C, and then the selectivities at the beginning and the end of the process, we should keep this in mind, right? What happens as the concentration of A goes down? So we'll get to that when we show plots. But of course, now we have the rate laws for A, B, and C. We have to find the concentration then of A, B, and C as a function of time. The other thing that we could do is find conversion. That's something that I do in almost every problem anyway. And just so you guys didn't forget, right? Conversion is the moles of A reacted over the moles of A that are fed. So the moles of A reacted are the initial minus what you have now over the initial number of moles, which of course, then this is just CA0 times V minus CA times V over CA0 times V. And so the conversion in this problem ends up being just 1 minus CA over CA0. We'll also calculate that. But before we do this, let's solve our mass balances, right? So our simplified mass balance with constant volume is just dCA dt equals RA, right? And that we correctly said was minus K1 times CA minus K2 times CA squared, okay? So we also then have dCB dt is equal to K1 times CA. And then we have dCC dt is equal to 1/2 times K2 times CA squared. Okay, so I'm going to open this up to you guys. How are we going to go about solving this problem and getting the concentrations as a function of time? What have we done before?
We've started with A and then just done like differential equations to try and solve for CA.
And so yeah, we've
that's-
tried to do this, right? To find an analytical solution to this problem. So we can try to do this. So here, this thing then just becomes dCA divided by CA times K1 plus K2 times CA equals minus dt, right? Can you guys all see how I got there? And then we integrate from CA0 to CA, and then we would go from 0 to T, and then we find our analytical solution and plug it in here, okay? So I did that. So I didn't remember the solution to that integral, off the top of my head. So I went to my calculus book, I found the integral tables and found that the integral of dx over x times ax plus b equals 1 over b times the natural log of x over ax plus b plus c. So here, x is CA, A is K2, and B is K1, right? I mean, if we just compare the two formulas, right? So I solved this. It took a couple pages of math for CA, okay? And CA equals K1 times CA0 over K2 CA0 plus K1 times the exponent of minus K1T divided by 1 minus K2 CA0 over K2 CA0 plus K1 times the exponent of minus K1T. Okay, so that was the concentration of A, solved analytically. Based on what we've done in class before, we would have then plugged that into those two. And is anybody super excited to integrate those, especially CA squared? Probably not, right? I know I wasn't. So I got to here, and then guess what I did instead? Anybody?
Euler's?
Yeah, exactly. Euler's method. As soon as I saw that that was the solution for CA, in fact, I got about halfway through the solution of CA and realized, oh, I'm definitely not doing this whole problem analytically, but I'm stubborn enough that I had to finish it. So I got to the concentration of CA and said, you know what? I'm just going to do Euler's method, because Euler's method is pretty straightforward, right? The implementation of Euler's method, if we said this was equation 1, that's equation 2, that's equation 3, well, it's much, much easier for equation 1 to say, well, delta CA is equal to, delta T times minus K1 times CA minus K2 times CA squared, right? And then to do this at a bunch of temperatures. And the same thing, right? The implementation of Euler's method into the second equation is extremely simple, right? It's just delta T times K1 CA. And for the third equation, delta CC is just delta T times 1/2 K2 CA squared. And that's very simple for us to do now, especially after you guys had all that practice in homework 1. I'm sure you guys are borderline Eulers in Excel experts at this point. And if you're not, don't worry. The homework next week will help you do that as well. And we can then find the concentration as a function of time. And CA follows the exponential decay, just like we would expect. And CB and CC both rise relatively quickly. And then after A is consumed, of course, the concentration in the batch reactor, also reaches an equilibrium value. And so one of the things that you can see, though, if you look at the bottom left-hand portion of the concentration plot, at the beginning of reactor operation, the concentration of C is actually higher than B, or at high concentrations, we're going to see that the selectivity is pretty poor. And that's exactly what we would have expected based on our conversation before we solved this problem, right? Because the selectivity here, or especially the instantaneous selectivity, has the concentration of A in the denominator. So if we have high concentration, we would expect there to be more C than B, at least instantaneously. And that's exactly what we see in the plots here. And of course, then we also see that the conversion of A increases as time increases, and eventually, because we have two irreversible reactions, that we reach one at some time in the future. Here, you could say it's probably around 70, 80 seconds, right? Where we get to a conversion equal to 1. So we have expressions now for the selectivity of our two species as a function of time, right? Where the instantaneous selectivity was 2K1 over K2 times CA, and the overall selectivity was just the concentration of B over the concentration of C. So let's look at that, right? So we were able to calculate the instantaneous and the overall selectivity. And just like we expected at the very beginning of life for our reactor, the selectivity is pretty poor. But as soon as we get to around 50, 60 seconds, well, you'll notice the concentration of A is very low. Suddenly the selectivity really increases, okay? And the relative rate of reaction for B versus C is low at the beginning, and the relative rate of reaction for B versus C is high towards the end, which is why at the end of life, we end up with a really nice overall selectivity, whereas it started at a value below 1. And that's exactly what you would have expected looking at this plot here, that at the very beginning, C has a higher concentration than B, and that's why the overall selectivity is less, okay? And so, here's a second example where we were able to calculate our selectivity. And one of the things that we found was that it depended on time, unlike the first example that was very, very simple. We also could do the same thing for the yield, right? Which of course we calculated in the last lecture as well. And here's a really good example where, the instantaneous yield of B is actually pretty poor at the beginning, which we would have expected. And the overall yield of B also isn't particularly great. So the portion of A that becomes B is around 60%. And depending on your process, that may or may not be acceptable. Okay. And if it's not acceptable, we have to do some more things, right? We could manipulate the concentration of A, as we talked about. We could manipulate the temperature. But if there's something I really want you guys to take away from the last 2 lectures that we had, where we're talking about yield and selectivity, is that in real systems, it is extremely rare to form only the product that you're interested in. It's really nice for us to write A goes to B, or A plus B goes to C plus D, and then we're going to sell C or D, and we're all going to make money, and it's going to be a wonderful thing. Oftentimes, you make things that you don't want, and you have to do separations. And in fact, it's a combination of phase equilibria, which with kinetics really is what separations is. It's like kinetics, phase equilibria, and separations are what separate chemical engineers from other types of engineers. And the thing I want to leave you with is that our class is a very important part of our chemical engineering curriculum. But I want to show you a plant. And this is the chloralkali process to produce chlorine and hydrogen gas from brine. And it's one of the, actually, it is the primary method to produce high purity chlorine gas in industry. And so being an electrochemical engineer, I like to show examples of electrochemical processes. So here's an actual electrochemical system that's used industrially to make chemicals. And on the left-hand side, these are stacks. These are the reactors. But the thing I want to show you is that, yes, that's one warehouse. But if you look at a plant, this building is this building. Everything else that you see in the right-hand image is for purification and separation. And I want to put our class into context a little bit, that, yeah, reactions facilitate what's happening, right? So the reactions are sexy, but separations are really what allow the chemical industry to exist, not just the chemical transformations that we enable.